Okay, good morning. Let's begin. Happy Friday to everybody. I want to remind you that we are not going to have our class uh, on Monday due to the Labor Day, so there is not going to be class. And next time I'm going to see you on Wednesday. Today I'm also going to post the new homework assignment, which is going to be due next Friday. And also today we're supposed to decide if we're going to have a quiz or if I'm going to collect the homework. So here is how we are going to do it. Now, one thing, because those people who are going to be joining Zoom section later, they cannot see what was already written in the chat. So there is a huge chance that through the whole section today, somebody is going to be asking, so do we have a quiz of homework? Please somebody type whatever is going to win again and again when needed, just due to the fact that Zoom has a strange structure of if you join it late, you do not see conversations before you have joined. So they cannot scroll up. It's not like they just don't see it. There is no history, which I find as something like pretty stupid. They should be able to see this history. Otherwise, it doesn't make much sense. But whatever, we are where we are, and Zoom works the way it works. I'm just explaining to you why we might have it. I was very frustrated at first until I got the understanding of why it's happening. No, you didn't miss the flip yet. Let's do it here. Okay, so now we are going to be flipping. Okay. Where is my flip? Yes, here it is. So ready or not, we are going to push the button, and they have pretty good success of 50% of heads and 49.97% of tails. So let's do it. I'm pushing. And homework it is. So the winner is the homework. What's going to happen is you have to submit it before 10:30 today. So hopefully many of you I saw already submitted it. Good for you. We're just going to grade it. Now, there is also a quiz, which is going to go live at 10:30 and going to be available till 9 p.m. What I'm going to do is I'm going to take off all the points. So right now, each question has some amount of points if you complete it. What I'm going to do is every question is going to be 0 points. And then the grade for the quiz is going to be 0. However, I still highly suggest for you to try and take it and just see how you do and then ask questions. Why do I suggest doing it? First of all, it's a good practice. Second of all, you will know what to expect when tail is going to win at some point of time, correct? Because it's going to be like, what did I prepare for you? And another thing is you're not going, actually, this time you're probably going to see the correct answers because I'm going to unmark the correct answer because there is no stake for it. But generally, when you take a quiz, you do not see correct answers. So it's only going to show your answer and say if it's correct or incorrect, okay? The reason for it is because I have the whole day for people to complete, and I do not want the rumors to go around and correct answers to fly. I want everybody to have the same benefit of not knowing what the correct answer is and do it. I just feel like it's more, how do I say, it's kind of better and more fair to everybody. Okay? But then if you have questions why you did something wrong, we definitely can discuss it in class. Okay, so last time we have been talking about for all n exists, and I see my chat is huge. So yes, everything is, homework submission is still 10:30 a.m. So you still have an hour to submit it, and you will have 10 minutes after the class to do it. This is why I said you probably want to have everything out there already and just either push the button or not push the button or push it anyway, because I don't mind if we do not grade homework, you're not even going to look at them. So they're just safely saved for you out there, and every time you need it, you know where to find it in case you lost the paper one. Okay, great. let's move on. So last time we were talking about quantifiers. So we talked about for all x, and we talked about exist x and how they're different. So this one, again, a reminder, is going to be for all x, and this is exists x, which is different, correct? Because exist means it's one or more, but at least one. And for all means no matter what we pick, we always get the property, okay? So we are going to go and talk about why we started with propositions, how we can use them, and why did we study all this like logic so far. The most important thing we're going to be discussing is implication. So I'm going to show you something. There are different ways to say P imply Q, and we're going to talk about it in a second. So we're in section 1.6, and 1.6 has rules of inherence. Okay, so first let's discuss P implies Q. We already said that the way to say it is if P then Q. But we also discussed there are some other ways to say exact same thing. First of all, not always people say if then. Sometimes they just say if P, they skip then and they just put comma Q, correct? That happens a lot. And that's going to have an exact same meaning. I can also say P implies Q, correct? It's still going to have the same meaning. Now, I can say Q if P, correct? I can say Q whenever P. I can say Q when P. English is a big language, correct? It has lots of different ways to say an exact same thing. You can say Q follows from P. We can say a necessary, and I have a feeling I misspelled it, and I did, a necessary condition for P. Wait, a necessary condition for if P then Q. A necessary condition for P is Q. And there are other ways. Now, when you talk about converse, inverse, and contrapositive of those things, you need to be very careful about it. So one thing I want to show you, because it is important, is that. Let's look at P implies Q. And inverse and converse are not similar, but I really want you to look at, and I actually need more space, so let me move it a tiny bit. I'm going to be doing a truth table for you. I want us to look at P implies Q versus not Q implies not P, which is contrapositive. So let's check why I want to see it. So P implies Q is going to be true whenever true does not imply false. True implies false is the only bad thing. Now, here is another way of doing truth tables. So what I'm going to do is I'm going to put my not Q underneath the not Q in red. So it's going to be F, T, F, T. So that's my not Q. Then underneath the P, I'm going to put the not P, which is false, false, true, true. And now in green underneath the actual application, I'm going to get the implies portion, which is going to be true, false, true, true. This is just another way of writing it. You can do it in like different ways. Now, if I look at this and that, what do you see? They are logically equivalent, correct? So contrapositive is logically equivalent to P implies Q. And we're going to be using it a lot. So this is why for proof writing, and this is why you really need it. So just to remind you, the first time we talked about like propositions and everything, I said it's important for you to learn how to do logic. And the reason for it is because when you write a proof and you're trying to show something to somebody, you need to do logical arguments. And one argument should come up from another argument. So pretty much one argument is going to imply another argument. And you need to understand what you can do and what you cannot do. Because sometimes a very easy flip is not going to give you what you want because it's actually not really logically equivalent. And one of the most common mistakes is if you have a statement like if sky is blue, then it is sunny. And then people are going to say, well, that's the same as to say it's sunny. So from something like that, they're going to say it's sunny. So the sky is blue. So somebody can say after that, it is sunny. So sky is blue. But is it true? No, it's not, because actually we know if sky is blue, then it must be sunny, but we don't know the other way around. And this is most common mistakes students are going to do as they're going to write proofs. And this is why it is important to understand that contrapositive is the same, but you cannot do converse, so do not flip. You cannot do inverse, do not negate, okay? So don't do things you cannot do. You also cannot say that it's equivalent to if sky is not blue, then it is not sunny. That's also wrong, correct? So if given that, you later say this or that and say it comes out of it, it's not really true. Does it make sense? Those are the things you cannot do. So converse and inverse are not the same as implies. So do not use it when you create your logical arguments. And now let's learn about what we actually can do. What are the rules of inheritance? Yeah, I like that this is a bad class to be colorblind. We can go to flying crocodiles. The idea here is it doesn't mean what exactly it says. It's just if you have a structure of if then, you cannot flip it and say it's still true. That's not correct, no matter what it says. And actually, I never said that if sky is blue, then it's sunny is true, correct? Sometimes sky is totally blue and it's not sunny at all, right? So it's not about the truthness or not truthness of my statement. It's about what argument you can derive from another argument, okay? Okay, so I have a question about the sky is not blue, not sunny. Let me check. No, the original, this is my P, and this is my Q, and this is my not P implies not Q. So how do we call it? What is that? It's not contrapositive. Contrapositive is negation and flip. And then here I didn't flip. Yes, this is the inverse. Okay, back. So now let's look at that. Assume I know P implies Q is true. Now, and assume P is true. The line, it's kind of like me doing a logical arithmetic. So I know P implies Q is true. I know P is true. And I want to decide something about Q. Can you tell me what can I decide about Q? Is Q is true or false? Q must be true. The reason for it is we know T, truth, implies Q, correct? And we know this whole statement also has value of T, correct? So that means we cannot put false because T implies false is going to give me false. So we must know Q is true. So the way we write it is you really do not need everything on half on this side. The rule of inheritance is going to look like that. So if I put arguments, I assume these arguments to be true. So now let's see. We can also flip. If I know P is true and I know P implies Q is true, is order important or can I still conclude Q implies P? Oh, Q is true. So those dots are kind of implies. Is it still true? If I know P and then I know P implies Q, can I decide that Q is also true? Yes, correct. The order doesn't matter here. They still both true, correct? So I still can have the same thing. Okay. So let's try and do it on the actual example. If you did homework, you then, I'm going to be precise, then you are ready for the quiz. And I'm going to assume some of you did homework, yes? And we know you did homework. So what we can conclude from it, correct? What I can decide from it is I can say you're ready for quiz. So if the statement, the top statement is true, and you did the homework, then you're ready for the quiz. So I can use this rule in order to create arguments. So I'm using this argument. What is an argument? So let's define it. An argument is set of propositions all but final propositions called premise the final proposition called conclusion. Now let's do an example. I am either CS or math major. This is my number one. Number two, I am not CS major. Three, if I am math major, I like logic. So what I want is I want you to prove me, to show me using the rules we have and we have studied that I like logic. So how we are going to do something like this? Well, first of all, we have a couple of things. I'm going to be saying P is going to be CS major. Q is going to be math major. R is going to be like logic. And now what I can do is I can combine what we already know. I can generate my sequence. So the very first one, representing using our logical rules, is going to be what? What is number one? Using PQR symbols. What do I have? I'm either CS or math major. P or Q, correct. Okay, that we know. We assume all of those propositions are true, yes? Now, what is 2? Not P, good. Well, what about 3? Oops, and I'm missing, I said it, but I'm missing the math here. Sorry. So we have Q implies P. Are we all in agreement? Math implies like logic. Oh, yes, Q implies R. I say R, right? P, yes, lovely. Okay, here we go. Sorry about that. Here we go. So now let's try and figure out what we know. We know P or Q is true, and we know not P is true. So what does it tell me about P? If not P is true, what is about P? P has to be false. So that's what we know. Now, so if we know P or Q and not P, what I can imply for it, okay, we know P is false. What can you tell me about Q? Is Q false or true? Q must be true, correct? So I can imply Q is true, correct? So this is where you can kind of say, well, it was obvious, yes? If you're CS or math and you're not CS, you must be math, correct? You probably already saw it, correct? But now I gave you an official way and explanation of why it is really happening. So we know Q now. So Q is true. And so another thing I'm going to know is I know Q is true, and I know Q implies R is also true, correct? And Q is true. Agreed? We know Q must be true. We know Q implies R is one of our rules, which we assume to be true. So what can you tell me about R? R is true? Yay? Does it make sense? Do you understand how we got there? Okay, great. So one more thing from section 1.6, which is important. Let's discuss about a couple of important things you can also derive, another of important rules. So rule number one we're going to talk about is universal instantiation. And what it says, that if you know what for all x, p, x, okay, can you still hear me? Yeah, okay, good. For some reason, I see some strange messages. Okay, so if I know that for all x, px, so I know all students did homework, can I then derive that John did homework if John is a student in a class and I know all students did homework? Yes, we can. So from all x, px, you can safely derive okay. I don't know. I think we might have some issues with electricity, so my connection is jumping a little bit, but okay, I think we're all good now. For all x, px, I can derive pc for some c, for one of the c's, correct? So pretty much I can pick up a c, which is a student, like specific name, correct? I can specifically pick one and say the property is true for him. So all students did homework implies Ashley did homework, okay? This is called universal instantaneous. Now, then we also have universal generalization. So for universal generalization, if I'm going to tell you that PC is true for arbitrary C in my domain, so pretty much I have a domain of, for example, again, all students. And I'm saying if I arbitrarily pick C, the property for him will work. I arbitrarily pick him and property always works. Then that means it must be true for everybody. So I can imply for all X, Px, because I arbitrarily pick C. That means I have a set and no matter who I'm getting out of it, he always meets the property. That means everybody must meet the property, correct? So this is universal generalization. Now, existential instantiation. So in this case, I only know what exists student who did the homework. What I can derive from here is I cannot now say John did the homework, correct? But I can definitely say something like PC is true for some C. So I cannot say it's now true for everybody, but I can say for some student, it's true. And this is existential instantiation. And then existential generalization. Is going to be if you know PC for some C, so PC is true for some C, then I can say exist X, P, X. So you can kind of see that instantiation and generalization, they're flipped. But the difference is in the first case, I say PC is true for arbitrary C. And then in the second case, we only have PC for some C, correct? So this is a big difference. There is like a huge difference between saying everybody do something and somebody did something. Okay, so for the homework from this section, you're going to do me question number 14. For that question, you're going to have some arguments already ready for you and conclusions, and you need to figure out what rules did they use. So open up the textbook, open up the tables. There are a couple of tables with rules of inheritance, and look which ones they imply. Here is the previous slide. And now we are ready to go and write some proofs. So the section 1.7 is called proofs. And we are going to learn what a proof means, and we're going to learn some vocabulary first. So let me first define a couple of keywords. So to go back for another look at the right side of my notes, section 1.6, question 14. So that's the only one you need. You only have one question. It's also going to be posted today on the icon, so don't worry about it. So theorem. What is a theorem? Theorem is a statement that has been proven to be true. So somebody proved something to be true, we call it a theorem. What generally it means is you do not need to prove it anymore, you can just use it. However, sometimes we do like to prove theorems or to ask you to prove theorems, and then you need to show why it is true. Now, axiom is a statement that assumed to be true, and it doesn't require a proof. Okay? One axiom is going to be 2 is a positive number. Do I need to prove it to you? 2 is positive number. Or is it an axiom? This is something everybody knows, but nobody can prove it, correct? We just define positives to be. This statement is an axiom. Lemma is kind of like a small theorem, pretty much. So lemma is minor result. Generally, long proofs are broken into lemmas. So you say, okay, first I'm going to prove this small result, and you prove it and you call it lemma. And then you say, now I'm going to prove another little result, and I am going to call it lemma 2. And then using lemma 1 and lemma 2 I already proved, I am going to prove the theorem. And this way my proof looks better and easier to understand because it's broken into the pieces. For those of you who have programmed before, it's similar as breaking into methods, correct? You can write a large, ugly program of 1,000 of lines, or you can try and make some structure to it and use some methods, and then people can look at the separate method and say, oh, I understand what this method is doing, and then it's easier to understand what the whole program is doing, correct? So lemmas is something like that in mathematics and a proof writing. Now, corollary. And again, all of them are statements. I just stopped writing it. But corollary, it's generally short result that concludes, from larger theorem. Okay. So axioms is something which generally never was proven. So axiom is something which doesn't need to be proved. We just believe it to be true. So it's not really that it was long ago proven. Generally, everything which was proven at some point of time, we can reprove it again. So it's a theorem. But axiom is something which does not require proving. Okay, next. What would be an example of corollary? You know what? You will see examples of lemmas and corollaries in a bit. Okay, so we will get there. In this course, we are going to be proving some theorems and some lemmas and some corollaries, and let's talk about it when we get to it. Okay, then you'll see it. But for now, those are just definitions for you, and you will see the use of it and how we break it. Most probably in discrete structures, you're not really going to get into any huge theorems, but if you, for example, studied calculus, what you can do is open up or search for the proof of integrals, how limits and not integrals, how limits and derivatives are connected. In order to prove it, you need a couple of lemmas first. It's breaking into the smaller results, and then it proves it. And then, yeah, I'll have to do a large example for you at some point of time. You know what? Let me find something in the textbook, and I will point you out to it, and I will also explain it as we go. Let's go then. Conjective. Statement that is unproven but believed to be true. If any of you have ever heard about an P problem, we're kind of thinking that P is not equal in P, so we feel it's a conjective, but nobody have proved it yet. But everybody believes it's true. So this is what conjective is. It's something which we believe to be true. And for those who like really into computer science, you probably heard about NP problem versus P problem, problems who can be solved in polynomial times and cannot be solved in polynomial times. And we believe those two are totally separated. They're not equal to each other, but nobody yet was able to prove it. Okay, proof. So what is a proof? Proof is a sequence of valid arguments the difference between axiom and conjective is conjective is unproven, but we are working on a proof and hope to have proof one day. And axioms cannot be proved or disproved, they're just taken to be true. Okay. One more. Definition. A number is even if it can be represented in a form and a number n. N is equal to 2k for some integer k. So let's talk about numbers first. So z is a set of integers. Those are positive and negative whole numbers. So 2, 5, 20, 100, million, negative 55, all of them are integers. We also have R, which is reals. Those are anything which can be represented as a fraction, real numbers. And in order for number to be an even, that means it's divisible by 2, correct? And what it means to be divisible by 2, it means you can do it as n equal to 2k. And yes, axiom doesn't need a proof. It's just true. Not believed to be true, but it's just the truth of itself. Okay, so the way to write it down is that we're going to say n, which is an integer number. It's only like makes sense for integers, is even if exists k, an integer such that n equal to 2k. So now let's unscribe. This little thing is belong. So n belongs to integers. And this is, as I already mentioned, is such that, and this is the last time I'm writing it. From now on, you need to get used to ST. Now, what is an odd number? The odd number is n in Z is odd if exists k in Z such that n is equal to 2k plus 1. From now on, every time you have even or odd number, that's what you need to have in front of your eyes, because this is the way you're going to be using your arguments. You're not going to go, this is even and this is, you will need to show everything using those notations. So first of all, read it, understand it, and second of all, I know you do not like the word, but memorize it. You're going to be using it a lot, and it's kind of making sense. So memorization is not a bad thing in this case. You're supposed to understand it and remember it, which is another way of like memorize it, right? So don't forget it. It's going to be important. You're going to be using it a lot. So now we are going to use proofs. So the direct proof, come on. Here we go. Direct proof is a proof when you just take P and show Q. You kind of derive directly. So I want to prove sum of two odd integers is even. Proof of, well, it's obvious, not going to work. I really need an official proof using official definitions I just gave you. So here's how the proof works. Let m, n be arbitrary integers. So in this case, they're arbitrary, remember? So and m, n are odd. Then exists k1, k2, and I'm going to be using this one, which are integers such that n is equal to 2k1 and plus 1, and m is equal to 2k2 plus 1. Let's look at the sum. N plus m mathematically is going to be equal to 2k1 plus 1 plus 2k2 plus 1, which is the same as 2k1 plus 2k2 plus 2. Now, remember my definition, the even number is number of a form 2 multiply integer, correct? So I need to show I can represent it as 2 multiply integer. So we are going to say 2, and I'm going to take it out of parentheses, and this is what we are going to get. let z be equal to k2 plus k1 plus 1. Z is integer, correct? Because k1 and k2 are integers. So now what we have is we have 2z here. Sorry, I need more space. And z is integer, so done. We proved it. So m plus n is even by definition. Well, congratulations. We did our very first proof today. And then next time we're going to keep on talking about different proof writing techniques. Have a good day.